So we want to switch to the next speaker by the Rantian, Anjan Rin, Masayoshi Tomizuka, and Rintin-san. And maybe Rantian is here.
Yeah, I'm here. I'll share my screen.
Oh yeah, thanks. Please go ahead.
Can you see my screen?
Yes. Looks good.
All right.
Wait, sorry. Yeah, now I can see.
It's good?
Yeah, looks good.
All right. So I will start. So hello, everyone. I'm Ran from UC Berkeley. I'm excited to present our short paper, negotiation-aware reachability-based safety verification for autonomous driving. All right. So self-driving technology has been advanced a lot in recent years, but we can still see that self-driving cars sometimes collide with human-driven cars. So it's very important for self-driving cars to have a safety verification module to monitor safety performance. And one of the methods is reachability analysis. So basically, given the traffic state, we model the interaction between the human-driven cars and the self-driving car as a pursuit evasion game, where the human tries to collide with the self-driving car. We also assume that in this pursuit evasion game, the human-driven car has full control bound, which means it can maneuver freely and not constrained by any other factors except its physical limitation. Then by solving this Hamilton-Jacobi I6 PDE, we can compute an unsafe set, which contains a set of initial states from which the human action can drive the joint system to some collision states, despite the optimal control efforts from the self-driving car. So once we have this unsafe set, there are a lot of ways to use this information for safety verification. For example, when the system is near the boundary of the unsafe set, the self-driving car can switch its control to the optimal safe control. Or the self-driving car can use this unsafe set as constraints in motion design module. But you can imagine that this unsafe set is very conservative since we consider worst-case scenarios. So the research question is how to effectively reduce the conservativeness of the unsafe set without sacrificing a safety verification ability. So when we compute this unsafe set, we assume that humans want to make collisions and have full control bound. We do want to assume adversarial humans because we want to consider scenarios that are worse than expectation in safety verification. But assuming human-driven cars have full control bound seems to be overly conservative. Because a human-driven car's control bound is really constrained by a lot of factors. For example, road geometry and the human driver's internal state. For example, in this traffic scenario, it's not reasonable to assume this human-driven car can use its maximum steering ability to cross the solid line and collide with the self-driving car. So if we can reasonably predict humans' control bound, then we can make the unsafe set less conservative, but still maintain a safety verification ability since we still assume human is adversarial agent just with limited control ability. One approach is to use a deep learning-based predictor to predict humans' future control bound. Then we can query an unsafe set for safety verification. One problem with learning-based predictors is that they cannot explicitly model negotiations between agents, and they struggle with robustness to out-of-distribution inputs and tail events. So the predicted human control bound may still be unstable and overly conservative in highly interactive scenarios. To overcome these issues, we treat the human as a utility-driven agent with a learned reward function. Then we use the leader-follower game to explicitly model the negotiations and infer the human's willingness to be negotiated. With the information about negotiations, we can correct the human's predicted control bound and further reduce the conservativeness of the unsafe set if the human is likely to be negotiated. To demonstrate how our approach can make safety verification less conservative, we extract an interaction from real traffic data. The red car is a human-driven car, and it always executes its original controls from the data. And the orange car is a self-driving car that executes its planned motion if safe. So in this experiment, we compute an unsafe set assuming the human has full control bound. As you can see that the self-driven car is stuck due to the overly conservative unsafe set, even though the human-driven car is willing to yield. So now with our approach, we can reason about how the human's control bound is constrained by environmental states like road geometry and human's internal state. So our method can dynamically adjust the unsafe set and give the self-driving car more flexibility. So the key insight is that in interactive scenarios, the distribution of human-driven cars control bound is not only constrained by environmental states, but also affected by the human driver's internal state. Estimating human-driven cars control bound online can effectively reduce the conservativeness of the unsafe set without sacrificing its safety verification ability. And in our ongoing work, we are trying to adjust the conservativeness of the unsafe site when our negotiation model cannot sufficiently explain the observations. And thank you.
Thank you very much, Ram, for your interesting talk.